The first thing you kind of have to talk about with any subject is the history of it. Now, why do we like to talk about history? Well, because history is what has made what we use today possible. What do I mean by that? What was the earliest mechanization? Anybody really know? Where we made a machine, made everything mechanized. Not steam engine, before the steam engine. Huh? Not so much the wheel. The Romans used to use basically a giant wheel and turned it into a treadmill, and people would walk on it and it would force it to turn. Clocks. Anybody ever seen a wind-up jewelry box or a wind-up clock? You all know what I'm talking about when I say that? Yeah? That is the earliest examples of mechanization. You're probably thinking, well, how can that be? Well, it's one of the first automatic things that occurred. Think about that for a second. Things that worked without a lot of human interference. All you had to do occasionally was wind it up and let it go. The clockmakers were some of the first ones to create mechanized machines. One of the more famous examples of this is that you had Leonardo da Vinci. He actually created a lion for the King of France. And it was a lion that could walk and it could roar. Sounds like what we use as a typical toy now, right? But he did it right in the age of a long time ago, right? So think about that. That kind of technology has been around longer than that. It's been around a while. So you cannot really talk about any subject without looking at its history and how did it all come about. And one of the first people you kind of need to meet is this guy.
George Devall's favourite place was his garage in Connecticut.
Pause that out and one thing I needed here.
Where ideas percolated and inventions were born. George Devall was a serial inventor. He was a guy who chose not to go to college because he was so brilliant that he was capable of making a living just by coming up with inventions on his own. By the mid-1950s, George had helped invent all sorts of devices, such as the phantom doorman that used a photoelectric cell to open doors. George Devall was kind of a nerdy guy who was really focused on the details. You know, he wasn't thinking about the big picture. He was really focused on how his inventions actually worked. And not so much on whether people would want to use them or what the applications were or anything like that, which is why he wasn't the greatest businessman. While looking through a technical journal, he saw an assembly line, an image of monotony that set his imagination working. George wondered, why should human beings have to do such mind-numbing work? You're doing that job again and again and again, and once you do it all day, things just lose concentration. And losing concentration meant that you could get injured, and people did. George thought that if something else were to do all the repetitive work, the workers' lives would be improved. If that tool were to move similar to the human arm, grab onto things and lift them up, its possible uses would be mind-boggling. It had to be able to pick up heavy parts. It had to be dexterous, so it had to be able to get a hold of those parts and hang on to them and move them to another place and let go of them. George pictured a machine that had a wrist that could bend and rotate similar to a real hand, with two opposing fingers to do the grasping. The arm's actions would be controlled by a computer, which could be reprogrammed for different jobs.
George obtained a patent, but he was unable to find anyone to listen to his idea.
He's really focused on details, he's really technically proficient, but he's not really very good at explaining what he's doing to anyone else.
His break came by chance at a friend's party.
George Duval, I'd like you to meet Joe Engelberger. I have a feeling you boys have a lot to talk about.
George, it's nice to meet you. You go. I think we need a drink.
Joe Engelberger was an engineer with a background in physics. He was also a very sharp businessman.
So, George, what line of work are you in?
Well, I had this idea. The two get to talking, and Joe suddenly realizes that what George is describing is something that he's read about in science fiction, only it's real, a robot.
Very interesting.
Joe spotted the huge business potential and all the possible uses for a robotic arm. It was the beginning of a fruitful relationship.
What do you mean, Joe? This is it. I know it doesn't look like much, but we can clean all this stuff out of here.
George concentrated on building a working prototype and solving engineering problems that arose. Joe began to identify all the potential uses and buyers for a robotic arm.
He was going to factories and he was trying to figure out the lowest hanging fruit. Where can robots help first? So he was trying to identify really important jobs for robots. And that means jobs that people don't want to do.
One of their biggest engineering
So before we go further on that, which did not mean to do that, what did they just say about what robots do? Because this is a sore spot for a lot of people when they talk about robots. A lot of people, what is the thing they say robots do? They don't say that robots help people. They don't say that robots are great. They say robots are taking what? They're taking our jobs. Now here's my thing, and I'll harp on this a lot during a lot of this because it is a point where nobody seems to realize they're not taking jobs per se. They're taking the jobs no one wants to do. And that's kind of why I wanted to pause that there, is because I know for a fact a lot of people tend to think, oh, robots are taking our jobs. Well, technically they're taking the jobs nobody wants anyway. Right? The jobs everybody has a hard time filling. Because who wants to sit there and stack something all day long? Who wants to have to lift heavy equipment and palletize it? And strap it down to pallets. Robots do a lot of the jobs that we don't want to do. And that's something a lot of people don't understand or think about.
He was going to factories and he was trying to figure out the lowest hanging fruit. Where can robots help first? So he was trying to identify really important jobs for robots. And that means jobs that people don't want to do.
One of their biggest engineering challenges was how to adjust the robot's grip so it was adaptable for different tasks. The solution was to install pressure sensors inside the machine's hand. The heavier the pressure, the stronger the grip was needed to be. The robot's movements were programmed into a computer.
You just move it through the motions, and then it would record that, and it would play it back again and again and again, all night long, never going to sleep, never asking for a break.
The prototype was called the Unimate. The duo continued to refine and test it, proving that their invention was adaptable to a multitude of tasks. It seemed as if success was inevitable, but George and Joe had not counted on the image that robots had in the US.
At the time, robots were just like witches or werewolves. They were completely made up. It was just like any other boogeyman that was used to scare people in a story. When robots appeared in popular culture, they were typically killing everybody. So this is a tremendously difficult business problem.
So typically when robots show up in a movie, they're killing people. Has that really changed? No. If you remember the movie I, Robot with Will Smith, it didn't change, did it? Mm-mm. Very cool. So even today, we still don't always think of the robot as the good guy, and we tend to villainize him, don't we? It's fun to do so. For God's sake. Keep doing that.
The US's lack of enthusiasm was disappointing. George and Joe had to expand their horizons, and in Japan, the post-war economy was booming.
In Japan, robots were much better perceived, and so there was no drawback for the Japanese companies to tell everybody, hey, we've got robots.
Japanese car manufacturers began to use Unimates, and productivity boomed. The rest of the world took note, and the robot revolution began.
This was a real turning point for humankind, because one minute we were just using tools, and the next minute we were letting our tools do their jobs on their own, completely autonomously.
In 2003, the Unimate was inducted into the Robot Hall of Fame. But it was George and Joe who deserved the real credit for working out that almost anything could be made with a robot.
Alright, so I said, just kind of give you all a little bit of history on a lot of this. So you have a motorized loom. Does anybody know what a loom makes? Huh? A loom is what makes fabric. Lots and lots of fabric. But having a person sit at one of those, what takes something mechanized maybe 5 minutes takes a human being, if it's a very intricate pattern, up to 5 days. Think about that for a second. So this one is a computerized, what you could almost call a computerized loom. I don't know if you can see the little holes here, but that's basically telling the loom what the pattern is. And it's doing it as it weaves the threads together. You have cam-operated lathe. This is the base of all modern lathes. You have a motorized crane. This is all the very beginning of a lot of this, right? A motorized crane to move, ingots, from furnaces, which is a very hot, nasty job, by the way. Y'all know what an ingot is, right? Think gold bar. That is technically an ingot. Y'all know what a gold bar, you see the big giant gold bars in movies, right? That is technically an ingot. Just a big solid piece of metal. Places like Sloss Furnace, US Steel, and things like that, they used to, the purpose of an ingot is basically transportation of metal. So what you do is you melt the metal, get all the impurities out of it, and then you create basically a solid piece of it so that you can send it somewhere else. It makes it easy for transportation. But in the process, you're having to heat the metal up to where it's almost boiling so that you can melt it down and pour it into these molds. Very hot, nasty work. So the term robot was first used with Karl Kapek's Rossum's Universal Robots, which is kind of an interesting play. If you ever have a chance to kind of look it up, it's really interesting in how they portrayed it. They even made it into a movie at one point. One of the very first computers, guys. Put it in perspective. This room would be filled with that thing. It's big. So it used 17,000, well, we'll say almost 17,500 vacuum tubes, a bunch of crystal diodes, relays, resistors, capacitors. It was roughly 27 tons. 27 tons. How much does your laptop weigh now? We're getting to the point where laptops and cell phones don't weigh anything. 27 tons for one computer. It took up 680 square feet. 600. That's not small. Okay? Now here's the funny thing. Guess what it could only do? It could only do basic math. It knew how to do basic mathematics. Couldn't really do more than that. Basically, this is an oversized calculator. Let that sink in for a minute. 680 square feet of oversized calculator. How scary is that to think about? How far we've come and what? This was 1946, so 60 years-ish. We've come a long way. Actually, it's getting close to even more than that. So, Cybernetics, or Control of Communication in the Animal and Machine, was published by Norbert Wiener. It's where he coined the term cybernetics. And it's all about the study of the machine and how it interacts with everything around it. Okay? Just kind of sum that up for you. John Parsons, first numerically controlled machine tool, worked with MIT. Which, if you ever get a few minutes, go to. There's an offshoot company from MIT called Boston Dynamics. If you want to see the latest innovations in robotics, they've got some really cool ones out. They've got one that looks like a little robot dog called Spot. They've got another one that looks almost human and can actually do a lot of programmed moves called Atlas, and it actually walks on 2 feet and is able to jump, run, and all sorts of things. I'll pull some of that up in a little while. So numerically controlled machines uses numeric codes to control the activity. So how many of you have ever used a lathe or any kind of machine that is computerized? Y'all know what I'm talking about? Where you set up what you want it to do before you get it to do it? This is the basic technology that started that. So if you ever wonder where a lot of this comes from, it started in the 1940s and 50s. And believe it or not, the technology has not changed that much. The main thing we've done is make things smaller. 1954, you have George Devol, which we just were talking about, who patented the first programmable robot capable of performing industrial tasks and creates the Unimate. His partner, Joseph Engelberger, helped him develop the Unimate. The first American company that this guy was put in, believe it or not, was General Motors. That was the first company. But before that, they were in Japan. Why? Well, because after the World War II, Japan decided it just going to try and catch up with everybody. Not just catch up, blow past us, right? We don't want to be second best. We want to be the best of the best. And even today, they keep coming up with a lot of innovations, and we are helping them out. We all work together and create better and better inventions. So General Motors, it handled die-cast machines, which again is very hot, heavy, nasty work. All right. So Stanford University, you have a tabletop robot arm powered with electric motors. So at this point, we've created the first robot. So now what are we going to do? Well, just like if you after you've created the first computer, what are you going to do? Well, you test it out, but everybody jumps on the bandwagon and starts making their own, right? Everybody sits there and goes, ooh, you're making money at that. I'm going to jump on with you. Sound about right? Not only are you making money, you're making money hand over fist because you're the only person that's created this. I'm going to create something similar and sell it just like you are. Kind of like the first car, right? The first assembly lines. Everybody sees what somebody else does and goes, huh, you know, I could do that. It's not that hard. Put a little capital in it, and all of a sudden they're making the same thing you were. Theirs is just a little bit different, right? You have Intel Corp that created the first microprocessor. This was for a cash register. So we're getting into where instead of using big computers with big innards, we're starting to do what? Starting to downsize the size, right? Because what if we don't need a computer the size of a room? What if we just need a computer the size of a laptop? Well, we got to find a way to start shrinking components, right? We want to maintain the integrity of what it can do, but we don't want it to take up a whole room. So we start finding ways to downsize. This is a T3 robot that used a microcomputer, and it was the first that could be programmed in a high-level computer language. We'll talk more about that as we go. I'll show you some of the programs these guys run. Again, this is all dealing with the microprocessor and the microcomputer is how can I make something smaller so that I don't end up having to take up more space than necessary? How do I possibly make sure that I get what I need done, but without taking up more space than I have to? Because what's the biggest problem with some of the bigger robots, you think? They take up a lot of floor space, right? That's a problem with a lot of machinery, right? It takes up a lot of floor space, which means that it needs a bigger building to be put in. Can't put a giant machine in a small room. It has to be in a big room, right? So if you can make things smaller and smaller, it's kind of like a phone. Anybody remember the oldest phones we used to have? The cell phones, the satellite phones? They were the size of a briefcase. Y'all know what I'm talking about? Yep. And it took forever to set it up so you could make a phone call. And even then, it was kind of iffy. Now, we carry that same technology that came out in the 70s and 80s. We carry that in our pocket. Think about that. We went from something about 10 times the size of this to this. Something that fits in your hand. Why? Because bigger, when you're trying to deal with machineries and mechanics, isn't always better. Sometimes you need a smaller area used. So this one is a programmable universal machine for assembly. Again, it was made by Unimate. We're going for smaller and smaller. And what we're starting to see, especially now, when robots first came out, they started off doing things like welding. Why welding? Anybody a welder in here? Has anybody ever done welding? A couple of y'all. What is the problem with welding? It's dangerous to your health. Why? Well, you have the flash arc, yes. What else? You can burn yourself. What about fumes? Those are very hazardous to your health, right? You start melting metal and fumes can be produced and those can kill you. Correct? So, do you ever want to weld in an enclosed space without ventilation? No. So think about the car, the modern day car. Think about what a welder would have to do to put all those welds in a car. Is that something a human wants to do? No. And the better thing about a robot is that they don't have to look through a helmet, right? They don't have to wear safety glasses. All they've got to do is come in, straight line, they're done. Now, what can a human do that a robot can't? Is that we are far more dexterous in our hands. So some of the harder places to get to, we can do better than they can. So welding was one of the first big ones. The second was what's called machine tending. Basically what that means is that it babysits something like a machine that's going to use a lot of heavy pressure, and once the part is stamped or it is created, it picks up the part and moves it elsewhere in the line. Now, why don't we want a human doing that? Well, 10-ton press. Enough said? Anybody want to put their fingers in that? Is the robot going to care? No. So we've gone from this society where we constantly did the boring jobs. We constantly had to do dangerous jobs, jobs nobody really wants, right? I was in automation for a little bit, and I remember one job we did. I tell this story a lot because to me, this epitomizes why we have made the switch to robotics. We had a company that came to us and said, hey, we're a gypsum plant. You all know what gypsum is? They basically break down limestone to create plaster. Does that make sense? So what they would have to do is they had these giant pressure cookers because the best way to break down limestone is heat and pressure. And it breaks it down real finely. So what they would have to do is crane in loads of rock, open the pressure cooker, dump the rock in out of this giant bucket. Now, any of you have ever had a bunch of dry ingredients packed in a bucket? How easy is it to make sure that everything comes out? Or do you sometimes have to tap the back end of it? Right? So what these guys had to do, in order to tap the back end of it, you had to take a sledgehammer, you had to swing it over your head and hit this bucket. So volunteers, how many of you'd want to do that day in, day out, 5 days a week for an 8-hour shift? How many of y'all want to do that? Probably not enough. So y'all see why we went to automation with that. So what we ended up doing was installing a pneumatic hammer on the back of this. And all that would do is come down, pop it a couple of times with the pneumatic hammer, and nobody's having to sling a sledgehammer. Which I can add to here. kind of see where y'all are going as, why wouldn't somebody just want to swing this sledgehammer? You make money doing that way. Well, think about what that'll do to your body over time. It'll break down your shoulders, it'll break down your back, then you have workman's comp injuries, all sorts of stuff starts adding up on that, right? And God forbid if you miss that bucket and hit somebody else. So that's the reason for automation a lot. Because it becomes a problem of HR can't fill the position, right? Because everybody sits there and goes, what jobs have you got open? Oh, we got this. No, I don't want to do that. You got anything else? Well, we're paying very handsomely for this. No, I still don't want to do it. You have people that it becomes too expensive to have somebody else do it. That's always a possibility, right? There's lots of reasons to automate. Okay. And again, it's a lot of people have come up. I've actually had people come up to me and I told them, I teach robotics. Oh, so you teach something that is going to take my job eventually? No, I'm teaching something that if your job is completely monotonous and does not really require somebody standing there and doing it. I'll give you for an example, screwing caps on toothpaste. How many of y'all want to do that? Ain't nobody wants to do that, right? That's a boring task. That's not something anybody'd want to do in their right mind. That's the kind of thing you automate. So it's not that robots are taking jobs, they're taking the jobs nobody really wants anyway. Right? And they have the ability to do it with a lot more precision than we do sometimes. So these days, we've even got them to where they work with food. This one's putting chocolate in boxes. This one is operating a foundry. Okay. These guys are welding. I don't know if you can see those welders very well. What about bomb disposal? That's a good use for a robot, right? Because who wants to walk up to a bomb and try and defuse it? Anybody? And we're just now getting started. We're really starting to get to where we can move things and do things. Heck, we can even do surgery with these guys. It is true. I know somebody that got surgery done with one of these. Okay? Any questions on all this, guys, so far? Yes, no, maybe so? All right, so let's go. So, real quick, what is a robot? How would you, if somebody sat there and came up to you and said, this is a robot, how do you define what a robot is? Anybody? What just happened? All right, so what is a robot? Anybody want to give me what they think a robot could be? Or do you think there is a precise definition of what a robot is? and yet we call them robots. So robot is a very broad term, correct? But it is a programmable machine that imitates the actions or appearance of intelligent creatures. In order to, the agreed upon definition, I guess you could say, is that it has to be able to get information from its surroundings, and it has to be able to move somewhere in the world. Okay? So, would y'all say that those have that ability? We have the Roboraptor that if you use the remote control, it has sensors so it can kind of get an idea of what's around it and it can react and have fun. But it can also walk. And then you have the little Lego robot you're going to build, which, by the way, this is exactly what you're going to be building. He's a little golfing robot. Yes, we'll begin to play with one of these. He has sensors, several sensors on him. He's got a distance sensor, which is an ultrasonic sensor. He's got a touch sensor back here. He's got a sound sensor, which is basically looking for as a microphone to pick up sound. He's got a light sensor, and he's got motors that can sense where they are. So putting that in perspective for you. He's able to move in the world and manipulate objects. Well, he can hit things with his golf club or run them over. Everybody good? So let me talk to you about ISO, the International Standards Organization. These guys define it as, and y'all might want to write these particular ones down or make note of these for later use. Excuse me. Because these are great test questions, aren't they? So the International Standards Organization say that a robot is an automatically controlled, reprogrammable, multi-purpose manipulator that is programmable in 3 or more axes. We'll cover what an axis is. A little. Okay? Everybody good? So yes, you do want this definition. And guys, I do have the slides available for y'all on Blackboard under the course content area, also known as lecture slides. Industrial robot. The way that these guys at the Robot Industries Association, that it is a reprogrammable, multifunction manipulator that is designed to move material, parts, tools, or specialized devices through variable programmable motions for the performance of a variety of tasks. So what words are in this one that were in the previous one? The buzzwords here should be reprogrammable and multifunctional. Why? Well, you'll see in a minute. But before we get there, all right, so reprogrammable and multifunctional, that was in both definitions. Reprogrammable, this is a machine whose actions are controlled by a stored program that can be changed by the end user. What do we mean by that? Well, that means that I can take a program for any single one of these robots and I can change it at any point in time that I want to. Multifunction is capable of more than one function. The great thing about most robots, and this is true of a lot of machines, but especially robots, I can put anything on the end of these robots and give them any job I want to, as long as it does not exceed their ability. Exceed their ability. What do I mean by that? Well, I mean that I cannot put 1,000 pounds on anything on any one of these robots and expect it to actually work. Okay? They are limited by their physical characteristics. Does that make sense? That is all. You know, I can't give them extendo reach, but I can work within the reach that they have. And I can give them any job. I can make them a welder, a painter, anything that I need to have them do. As long as I do not exceed their physical capabilities, they'll do it. All I have to do is put the right tool on the end of the hand. Okay? All right, everybody good? I'm sorry about the whiteboard versus the whiteboard, guys. The whole purpose for one over the other is that the other board's not exactly clean right now. So we've been using this to feel a good clean surface to read off of. The other board, we're hoping to get it replaced soon. So it is not, it must have several of the following. It is not natural or has been artificially created. It can sense its environment. Now this one is tricky. And there's a reason I say that. There are two different types of motors that are generally used. There are servo and there are non-servo. Servo motors provide feedback to the robot as to what position they are currently turned into. Okay? Non-servo motors are most often things like stepper motors or the motor in your car. Do you think the motor in your car knows what position it's in at any one point? No, it doesn't. So, in a way, a robot can have a way to sense, but it only can sense itself. What makes robots so dangerous sometimes is the fact that we have external sensors that we create and use to work with the robot. The problem is, all it ever takes is tripping that sensor and the robot takes off. Why is that a problem? Well, if you happen to be up on the robot trying to work on it, or you're just working close to said robot, and you accidentally trip the wrong sensor, what's going to happen to you? You won't be happy the next day. Put it in perspective for you. That robot right there, if you got him going fast enough and hard enough, he could sling you through the wall. Very easily. He don't care. He doesn't even know you're there. He knows what position he's in, but it's kind of like somebody who's blind. Okay? They know where their body is in relativeness to them. Does that make sense? Like, I know where my hand is at all times. Why? Because my hand is attached to me. I know where my legs are at all times because my legs are attached to me. Do I know where they are in relation to the rest of the world or to anything that's in that world? If I'm blind, no clue. And it's exactly what a robot is seeing. We add sensors to give them the ability to detect things around them. So in other words, we give them better hearing with sound sensors. We give them ultrasonic sensors so they can sense if there's a distance between them and something else. We give them light sensors. We give them touch sensors. We give them all sorts of things to allow them a little more knowledge about the world around them. But at the end of the day, they're still the blind person standing there going, okay, I have no idea what's around me, but I know the task I'm supposed to do. Does that make sense? I will say this, if you do nothing else in life with a robot, respect the robot. What I mean by that is the robot may be sitting like that and just sitting in its perched position. But the reason you respect the robot and give him a lot of room to move is because at any point in time, somebody trips that sensor. If you don't have the respect for the robot and give him the room he needs to move, you're going to hurt. Might not be anything more than a few bruises, but you're not going to be happy the next day. Make sense? So sensing its environment, we tend to think robots have the ability to truly understand the world around them. Don't let anybody ever tell you they can do that, and don't ever be fooled that a robot can. We can make it seem like it, but it cannot tell you're there. Okay? Does that make sense? It can manipulate things in its environment. Very much true. Has some degree of intelligence. We'll talk about what intelligence is as it applies to robots. It is not the intelligence we give to humans. It is the level of complexity of the computer that is attached to the robot. Does that make sense? So it has some degree of intelligence or ability to make choices based on the environment or automatic control or pre-programmed sequence. So again, we'll talk a lot about a lot of this. A robot must be programmable. Simple enough, right? What use is a machine if we cannot tell it what to do? It's a nice, giant, very expensive paperweight. Right? Can move with one or more axes of rotation or translation. Now, axes, it's not the first time they've said that. Axes are the joints by which the robot is able to rotate or move along. Okay? So, for humans, we technically have 3 axes in our arm. We have the shoulder, which can rotate, but our shoulder can also do what? Move up and down, yeah? In order for the robot to have that same ability of movement, it has to use not 1 axis, but 2. It has the ability to rotate that around that base, and it has the ability at that shoulder to move in and out, or up and down, rather. Okay? They have an elbow joint that is very similar to ours. It just moves in and out. Okay? And then they have 3 joints to do what our wrist and our arm can already do. Okay? So I want you to think, how hard is it mentally to sit here and go, okay, I need to pick up the book. So I need to reach out with my arm. I'm having to move my shoulder and my elbow in sync. Yeah? And then I put my arm down and I'm able to twist my arm enough that I can grab this and pick it up. All right? With a robot, you have 6 axes to make it do the full complexity of what a human arm can. Because in their wrist, they have the ability to move up and down, the ability to move left and right, and they have the extra ability that we do not have to rotate their wrist. When we rotate our wrist, we tend to rotate a lot more of our arm than just that wrist. So axes are each joint that has the ability to move either rotational or linear. By linear, that means straight line. It can make dexterous coordinated movements and appear to have intent or agency. Now, I like the word appear here because, again, it goes back to we tend to give these things a lot more credit than what they have. Okay? If this thing moves like it's intelligent, it's only because the computer program that was created with it gave them the ability to appear intelligent. Okay? I'll show you some robot examples one day that make it very apparent that things have changed. So robot classes, y'all definitely want to write this down because there are 4 classes of robots. You have a class A, which is devices with manual control. So think crane operator, right? Think machine operator, where every time you want the machine to do what it needs to do, what do you got to do? You got to push the button or pull the lever. You have to turn the wheel. You have to do something. It has to have an operator right there babysitting it. Okay? Does that make sense? You have a class B. These are automated handling devices with predetermined cycles. So your very basic machine. So this might be something that's just bringing toothpaste caps down and screwing them on the toothpaste. It has the same cycle over and over and over again, and it does its job day in and day out without stopping. Generally, these are for very monotonous tasks, ones that do not change over time. Mainly because changing those particular ones tends to be a job and a half. Why do I say that? Well, because unlike, let's say, a car, because a car, how much do cars change from year to year? Every year, right? They make some small little minor change, at least. Believe it or not, those minor changes are a big issue sometimes with people that have to program these things. Because that small minor change could mean that instead of, oh, I'm just having to move a couple of points, it can mean that you have to scrap your whole program, start again. Because now, because of that small change, none of the points line up and you've got to redo everything. Excuse me. So there is, so with automated handling devices, the reason we like those for repetitive jobs is because they can do it repeatedly without problem. However, changing those is probably one of the biggest royal pains you will ever come across. Y'all know the machines I'm talking about. They're the ones that anybody sits there and says, well, we have a new thing that we're going to have to do with this, so we've got to start changing parameters. You have to get so finicky with these to within hundredths of an inch that it takes forever to fix it. Yeah? You have a class C. These are programmable servo-controlled robots with continuous or point-to-point trajectories. And the class D and C are almost identical, okay? These can be classified as class C or class D. If y'all saw the little red robot that was sitting in the middle of the room, he is technically a class D, and I'll tell you why. These guys, again, they're the blind person that's just, I'm standing right here, I have no idea where I'm at in the middle of the world, I have no idea where anything is at around me. Why? Because I have no ability to see. If my servo motor's engaged, I don't know if there's something there. Okay? I can see nothing. That particular robot, the little red one, his name is Sawyer. He's a brand new one. He's what's called a collaborative robot. And he actually has a lot more intelligence. His servo motors, if he encounters any little bit of resistance in the world around him, he knows that there is something there, and he stops. He sits there and goes, oh, my bad. You're there. Sorry. And he stops his program at that point and says, okay, I'm not going to move until you're out of the way. So he's a class D, and the others are more of a class C. Now, I can add sensors to these class C robots and move them into a class D. That's the only difference between a C and a D, is that one has a lot of sensors, the other one not so much. Do we always have to have sensors? No, not really. Because if I'm just using this thing as a forklift to move, let's say, pool water heaters, and be able to pick those suckers up, put them on a pallet, spin the pallet, and wrap it, let it go, I don't need to know everything else in my environment. However, if I'm working very closely with, say, a human, or in close proximity to things that are around me, I might want some more sensors on it just to make sure that it doesn't bump into anything, right? All right, the International Federation of Robotics. Now, these statistics are a little bit old. By old, I mean kind of old. So, the IFR indicates a record-breaking number of industrial robots are being installed worldwide. In 2014, the sales increased to 29%, and industrial robots numbered 1.5 million machines in 2014. With an estimated 1.3 million additional robots to be installed by 2018. Again, some of these numbers are a little bit old. I've been trying to get back into where all this came from, but currently they have not got the current statistics out. Robots enable manufacturers to reduce direct and overhead costs by making dramatic difference to your competitiveness. Now, what does that mean? Well, it means that, unfortunately, humans like to be paid, robots don't. But again, most of the time, it doesn't even have to do strictly with that, okay? Because it also goes back to, how many of y'all have ever been hurt on the job? A couple of y'all? What do you always end up having to go to is you have to go talk to workman's comp, right? If the injury is severe enough. That's how it takes money out of it, right? We go back to swinging a sledgehammer over your head. Eventually, you're going to tear up your back. That's a workman's comp injury. That means that they've got to shell out a lot of money to take care of you. Think they want to do that? So if you get rid of those kind of jobs and make it where all somebody has to do is really kind of follow this machine around and make sure that everything's working okay, you don't have to worry so much about that, and you save a lot of money. That tends to be the whole point everybody wants to make about robots steal our jobs. No. But they do actually keep costs down. Right? Does that make sense? Everybody kind of hanging in there with me? All right, so this is a couple of assembly robots. Okay. All they're doing is working an assembly line and kind of working together. So some manufacturing terms, and some of y'all might have heard some of these, some of y'all might not have. Mass production. This is something that's kind of starting to disappear. Mass production means that instead of waiting for customers to actually order something, you create a bunch of stuff and then go let it sit in a warehouse for a while until somebody decides to order it. This particular model has actually been falling that by the wayside a lot more as time's gone by. As time's gone by, mass production has kind of fallen by the wayside. Why? Because it tends to tie up a lot of your money in inventory. Does that make sense? So then you have what's called batch production, just small quantities of different items. So instead of just running one giant production of everything and just kind of going, okay, let's say toothbrushes. How often do any of you buy a new toothbrush? About twice a year? Maybe a little more often, a little less? What? Do you buy one every week? So is there a point in making 2 million toothbrushes just to go sit them in the warehouse? Probably not, right? Or something else. I'll get where I'm going with it. So batch production, you're creating smaller quantities of it, and you're creating different items. You're trying not to have a large inventory. Why? Because inventory tends to really sink a lot of money into things. And then you have hard automation, machines that are designed and built to run a single product. These are not reprogrammable, and any adjustments are very hard to deal with. And by the way, guys, just so y'all feel a little bit safer with robots, there's only been about 33 deaths in the past 30 years. So about one death a year. In other words, you're more likely to get struck by a tornado. Right? More likely to get struck by lightning. These are actually very safe. I always try and overemphasize it just because a lot of people, I hate to say it, but not everybody is smart when they're around heavy machinery. How about that? If you don't pay attention to what you're doing around heavy machinery, it will come back to bite you. Last thing I'll say on that. And most of the time, it's not even you don't have a lot of fatalities in it. So, okay. So hard automation. And I can give you an example of hard automation. Going back to automation, whenever I was working it, we had a machine that would just screw bottle caps onto bottles of like apple juice. You know the character heads apple juice drinks that you see in the grocery store? They have like the Disney princess or Shrek or whatever. Our company had built the machine that screwed those caps on. That's hard automation. Why? Because all that machine does is bring the cap down, screw it on, let the juice ride. That's all it did. You can't really reprogram something like that. You just have to keep replacing the parts. If anything changes, it is very, very, very hard to get it to do what you want to do. So you have project shops, you have job shops, batch work, repetitive work, and continuous work. So project manufacturing, these are one and done. Okay? This is all about things being made to order. So think about what's a company that makes one car for customers customized? Not Tesla. Tesla. Huh. Okay. So I guess you could use a Tesla. Another one you can also use is anytime. How many of you have ever put your car in the shop to get it repainted? That's a project shop, right? It's a one and done. It's a specialty project specifically for one customer. Okay? So, one and dones. This isn't a lot of heavy manufacturing. In fact, I won't say that. So this is a type of manufacturing that just is a very quick, very easy, get it done, get it over with. Then you have the job shop. Okay? So this is where you're producing small batches of lots of things.
When a highly specialized product is needed in very low volumes, usually on a customer order basis, the process generally used is called a job shop. A good example of this is a tool and die shop. In the tool and die shop, precision metalworkers manufacture durable, customized tools that are used to stamp out parts, forge steel, or act as a mold for liquefied metal or plastic. The equipment can produce a wide variety of parts in very low volumes. In this example, a special stamping tool is required to produce engine gaskets. The tool designer receives the specifications from the customer and designs the part on computer-aided design or CAD equipment.
By the way, anybody see those computers? Anybody else feeling like that's about the most ancient computer you've seen in a while? Yeah, I think this was made back in the 80s. Yep.
And designs the part on computer-aided design or CAD equipment. The CAD equipment allows the operator to quickly design an almost endless variety of products in a very short period of time. From here, the machine shop begins to grind the metal into the required dimensions. Holes are drilled and tapped, and the pieces are locked in place. This one-of-a-kind tool is now ready to be tested, and sample parts are stamped out using the new tool. Precise testing and measuring equipment ensures that the specifications have been met. In each step of this process, the equipment used could also be used on a wide variety of other machine tools. Because every project is custom-made, the equipment must be flexible enough to change with each new job. But since producing a large volume of product isn't necessary, the process can be geared toward providing an exact custom product.
There you go. Job shop is more about the custom product, but it's also about flexibility. And this is what machine tending looks like. So robots, the really kind of cool thing is not only can they have 6 axes, they can actually have a 7. And that's where you add it to a rail.
Designed this new automation concept for a series of camshaft machine centers that traditionally use separate linear motion gantry-style pick-and-place mechanisms and floor conveyors. This new 7th-axis robotic
Sounds very excited, doesn't he?
Hispanic R2000 IB rail-mounted robots reduces the amount of fixed automation equipment required, cuts 4 individual automation systems down to 1, uses less energy, and frees up floor space while providing capital equipment flexibility. By integrating these top-loader Fennec R2000 IB material handling.
Okay, I don't want him to send you all to sleep. This is flexible manufacturing.
The Flexible Manufacturing Cell, FMC. This is the individual automated manufacturing unit in your company. The size is determined only by your requirements on productivity and throughput times. Here, for example, you can see me in operation in a large milling cell, in which up to 4 different milling processes can be carried out simultaneously. This demonstrates that I don't have my name without good reason. I adapt myself all the time to every situation. And how does this benefit our customers? Superb cost effectiveness. Automated handling with me, the chameleon, is efficient in every extension stage of your manufacturing cell and always a sound investment. Because I have a consistent modular design. This enables a completely relaxed look into the future, not only for...
All right, let's keep going on that. All right, so that is very loud. All right, so all of these is just kind of showing y'all some different ways that they do machine handling. So you have what's called continuous manufacturing, okay? We were kind of talking about it a second ago, but this is very large volume and low variety. Somebody misspelled. Specialized equipment performs a narrow range of functions very efficiently, but it does not usually use robots. Why? Because robots are very flexible. Why would we want to use something highly flexible for something that is not? Okay? So with a job shop, you want high flexibility. The cost is very high though, and you have very low output volume. With batch work, you have moderate flexibility, moderate cost, very low output. If something's repetitive, it has a high output, keeps everything else low, but the flexibility is low itself. Continuous is probably the cheapest way to go. But like we said, if you have a car company like Mercedes, do you think they want continuous? No, because they change minor things about everything every time you turn around, right? That would cost them a lot more to try and re-change everything every time something needed to be changed. Does that make sense? Yeah. So here we go with some robot welders. So how much precision do you think a human could do with that? Day in, day out, 5 days a week, 40 hours a week. Be a lot harder for us to do it, right? And then you not only have one person doing all this, you have multiple people that are having to do all this, right? There's no way you can have a team of what, 6 people trying to do all this at the same time without getting in each other's way and without making mistakes. The angles are awkward and everything else as well. And there's something none of us want to handle, right? What is that? At the very least, you can tell that it is a very hot metal. Who wants to go start grabbing hot metal? Anybody? Nope. Didn't think so. All right. So go ahead and head into safety a little bit. Most accidents occur during programming, testing, inspection, and repair. In other words, anytime you're up close to the robot, where does your mind need to be? Does it need to be on lunch? Does it need to be on what you're doing after work that day? Where does your mind and your focus need to be on? We've been working on that robot. I'm going to pause this out. So you step into a robot's workspace, you should always have very healthy respect for what you're stepping in the cage with. Okay? Always have a healthy respect for what you're looking at. One of the things we have to deal with is safeguarding. Okay? We have the new robots like collaborative robots that you can get up close and personal with. You don't have to have safeguarding because they have safeguarding built in. The giant industrial robots, you don't get in their space. Not without a lot of safeguarding, and you really don't want somebody in their space in general without a lot of safeguarding around them. You have to have a lot of training to deal with these. Why? Because training keeps people safe. Training reminds people that, hey, what you're about to do is not a good idea. Okay? This is ruled over by ANSI, which is the American National Standards Institute, the Robotics Industries Association. They created a rule called R1506 of 2012, and you also have to deal with OSHA. But the thing is, most companies have their own set of rules for these, and those are the ones you really want to make sure you follow. So work cell design. So what is a work cell? A work cell is where we put a robot so that it can do its task without interference of humans and without humans getting in its space. Does that make sense? So it's designed to around the task the robot is supposed to perform. It has to take in location of the robot, the startup and programming procedures, normal mode of operation, malfunctions and corrective actions, energy hazards, and shutdown, lockout, tagout procedures. We have to consider all of these things whenever we're creating these cells, much less when we're working in them. Okay. Safeguarding, one of the biggest things we have are fixed barriers around these guys. We put up fencing to make sure that people don't just randomly walk up and try and get in the cage. Because we put these guys behind a cage. Why? It's kind of like, why do we cage wild animals at the zoo? Because you just know somebody wants to get in the cage with the lion. Right? They don't always think about it. They just kind of walk in the cage with the lion and go, hi, lion. Right before the lion does what? Right before the lion eats them, right? You have interlock barriers. What are interlock barriers? What do y'all think? All right, if you look at these work cells, you see the little red thing up in the corner? Those are called safety interlock. Basically, they're locks that are part of the system that whenever you disengage those locks, it shuts the work cell down. Because it says, hey, intruder in the area, watch it. Don't touch the person. You have presence sensing devices. You have e-stop buttons, you have brakes, you have awareness devices, and warning systems. The presence sensing devices, how many of y'all know what a light curtain is? That is a presence sensing device, and we will talk more about those as we go through all this. Okay, so this is a robot behind its cage. Basically, keep everybody out. Some different ways that we do this. We have the guards, mesh. You have latch out controls. You have mirrors with light beams. You have safety mats. It all depends upon who the company is and exactly what they want to do as far as going above and beyond the basics. The basics is you put a cage around it, you make sure everything's in reach of the robot, and you let it go. The more complex of it is that, hey, you might actually have to have somebody come in every now and then and work around the robot. And whenever they're there, you have to make sure that they're safe in that space. Okay? Because I've seen some videos where people actually get in the area with the robot, and the robot will hold and pick up heavy stuff so the person can get in under and around it. You know, say a motor. Well, maybe I need to go install some stuff on the bottom of a motor, but I don't want to have something that flips the motor over that could damage it. So I use a robot to pick that motor up, and the human can go and work around that motor to fix and inspect things. All right, show you some examples of control devices. All right, so, and that is that for that one. So I'm going to